this is a key for the Unit 14 review. For these first questions here, you can kind of just read over the answers, and I think that they kind of make sense just in and of themselves. So those are the definitions. Make sure that you know those for the exam. In terms of solid solutions, liquid solutions, and gas solutions, what makes something a solid solution is if it is something that's dissolved or mixed into a solid, and something that's a liquid. So I'm saying like the solvent would be a solid there. If it's a liquid solution, the solvent is going to be a liquid. If it's a gas solution, the solvent is going to be a gas. And so I've given you a variety of examples there. Maybe try and familiarize yourself with these examples. You don't have to memorize them, but just knowing what's a gas solution, what's a liquid solution, things like that. That sort of thing might come up on an exam. So make sure that you're kind of familiar with that concept. These are the three ways that you can dissolve something faster. Mixing it up, what that does is it's moving all the water particles past the solid crystals. And so as the water, or whatever the solvent is rushing past the crystals that you're trying to dissolve, it pulls away at the edges because there's sort of a friction there, and it makes it dissolve faster. If you heat it up, all the particles in the liquid are moving faster, which means they're moving around more, they're hitting the sides of the crystal faster, things like that, and that increases the rate that things dissolve. And then crushing something up, because if you have something that's in a large chunk and you drop it in a solvent, it's not going to dissolve very fast. Just particles are going to be coming off of the surface, but all of the inside of that clump of whatever is not in contact with the solvent. So if you crush it up and make it into a powder, then you have a much larger surface area that's in contact with the solvent, which means more of it can go into the solution faster. This phrase, like dissolves like, what that means is that things with similar polarity are going to dissolve in one another. So if they're nonpolar, they're going to dissolve with each other. If they're polar, they're going to dissolve with each other. But a polar and a nonpolar substance don't mix together. So that's a really, really big concept with solutions. So know that like dissolves like, or polar substances dissolve polar substances, and nonpolar substances dissolve nonpolar substances, but they don't mix together. That's why oil and water don't mix. For the cyclohexane question, so again, this is just going with that like dissolves like. Cyclohexane's nonpolar, oil is nonpolar, so those are going to mix together. Soap. So the way that soap works is soap has different parts of it. So it's got this hydrophobic tail and this hydrophilic head, and what it does is it makes like sort of a three-dimensional sphere surrounding grease particles or oil particles or whatever you're trying to get out. And so whenever we're using soap in our lives, when we're doing the laundry, when we're doing the dishes, it's because we're trying to dissolve a nonpolar solute into a polar solvent. And soap really helps with this because it's got polar ends and nonpolar ends. And so it makes sort of like a three-dimensional sphere barrier around the grease, and then it helps to carry it away. And so soap, I think, is actually really, really interesting in that way. It's sort of bridges, the gap between polar and nonpolar here. Number 7, so here, electrolytes conduct electricity, non-electrolytes don't conduct electricity, and this has to do with whether the electrons that are moving into it have the opportunity to bounce from place to place and move through the solution. Electrolytes are generally made of ionic substances, so you have to identify that the solute is ionic, which means it has a metal and a nonmetal. And so if it's something like sodium chloride or calcium chloride or sodium nitrate, something like that, any ionic substance, and you've got it dissolved, it's going to be an electrolytic solution. If it's two nonmetals, so like glucose sugar or sucrose sugar or something like that, it's a covalent molecule, then it's going to be non-electrolytic. So supersaturation, I talked about this a bunch of times in class, but the way that you make a supersaturated solution is that you have to heat it up, dissolve a lot of solute in there, and then cool it down. And you can't just get this by adding excess solute. If you're just adding solute and you get to the saturation level, any extra solute that you put in is just going to sink to the bottom of the container and not mix in. So the only way you can do this is by heating it up, dissolving a lot of solute in there, and then cooling it back down. All right, this is talking about the Van 't Hoff factor and how many pieces something's going to break into. So this also has to do with electrolytes and non-electrolytes. So KBr here, that's ionic, so it's going to split into two pieces. Benzene just has carbon and hydrogen, so that's a covalent molecule. It's nonpolar, it's a non-electrolyte, so it's not going to split up, so that will just be one piece for benzene. SNF2, that's a metal and a non-metal, so that's ionic, so it's going to split up. And so it's going to be 2 for the Van 't Hoff, or sorry, 3 for the Van 't Hoff factor for that. For questions 10 through 13, it says that you have to use the solubility graph, so that's on lab 44. It also should be on your practice exam, so those are some different places that you can find it. So number 10 here says, what's the maximum number of grams that can be dissolved in 100 grams of water for the following substances and temperatures? So what we're doing here is we're looking at where the level of saturation is for these different ones. So the first one here, ammonium chloride at 50 degrees. So we go here, we find ammonium chloride, and we find 50 degrees. So you kind of just trace up 50 degrees, and you find that ammonium chloride, it looks like it's right here, okay, and so that looks like it'd be 50 grams. For that one. If you do the same for NaNO3, and this NaNO3 is at 25 degrees Celsius, so we find 25, we find NaNO3, it's right here. You see that that looks like it's 90 grams. Okay, and then one more time, KClO3 at 20 degrees Celsius. So we go to 20 degrees Celsius, we find KClO3, it looks like it's right here. That is 10 degrees, or sorry, 10 grams. This next part here is a little bit different. So what this is saying is we actually have this much dissolved. So we have, for instance, in A, 50 grams of KCl dissolved at 20 degrees Celsius. And it's asking us if it's saturated, supersaturated, or unsaturated. So what we do is we find the point 50 grams and 20 degrees Celsius, and we see if it's above the line, on the line, or below the line. If it's above the line, it's going to be supersaturated. If it's on the line, it's saturated. If it's below the line, it is unsaturated. So we're comparing it to that line for KCl. So yeah, we'll go find 50 grams and 20 degrees on this chart. 50 grams, 20 degrees, that's right here. Oops, that's the other way around actually. Let's go 50 grams here, 20 degrees, that's right here. All right, and we are looking here for KCl. So the KCl line is down below it. You can see if you trace it over, it's this line here. So that means that this is going to be supersaturated. All right, let's get rid of some of these dots. The next one here, it says we're looking for 100 grams of KNO3 at 60 degrees Celsius. So we find 100 grams. We find 60 degrees Celsius. So that is right here. This is below the line for KNO3. It's that line that's right there next to it. So that means it's unsaturated. And then the last one, 126 grams of Ki at 0. So 126 grams, that looks like it's like right here. For Ki, that looks to me like it's right on the line. So that would be saturated. So fill those in. This one was supersaturated. Uh, 100 grams of KNO3, that was unsaturated. And this last one was saturated. Number 12, what would happen if you mixed 50 grams of solid Na2SO4 into 100 grams of water at 20 degrees Celsius? So here we got to see how much would dissolve in Na2SO4 at 20 degrees Celsius. So Na2SO4 at 20 degrees Celsius, it looks like here. So we could dissolve something like 54 grams. I asked what would happen if you mixed 50 grams in. So since we could dissolve 54 grams in there and we're putting 50 grams in, what would happen is all of it would just dissolve, okay, because we haven't reached the saturation point yet. For number 13, what would happen if you mix 70 grams of solid NH4Cl into 100 grams of water at 50 degrees Celsius? So this one, again, we have to figure out how much is going to dissolve, how much NH4Cl is going to dissolve at 50 degrees Celsius. So 50 degrees Celsius, NH4Cl, that's right here. It looks like 50 grams will dissolve. And so if that's the case, then if we put in 70 grams, the first 50 will dissolve. And the rest is going to sort of settle to the bottom of your container. And now onto the calculations. So here, this first one, it says, what's the molarity? 35 grams of KCl dissolved in enough water to make 200 milliliters of solution. So for this one, it's asking for the molarity. You have to know that the molarity is equal to the number of moles of the solute over the volume of the solution. Okay, so we have to get the number of moles of solute then, because we're given 35 grams of KCl. So we say 35.0 grams of KCl. And then you look up on the periodic table the mass of KCl and you get 74.55 grams in 1 mole. Multiply those, you get 0.469. And that's moles. Okay, and then to calculate the molarity, molarity equals, then again, number of moles of solute, so 0.469, over the liters of solution. And so this says 200 milliliters, but we need to change it to 0.2 liters. Okay, and we end up with 2.35 molar as our concentration. Number 15. So this one here says you're trying to make 50 milliliters of a 1.5 molar H2SO4 solution, but you start with a stock solution of 8.0 molar concentration. What volume of the original solution will you need, and how much water will you be adding to it? So on this one here, we're starting out, it says that the stock solution or the original solution had a concentration of 8.0 molar. It asked what volume of that we needed, so that's V1, it's unknown. We know that we're trying to make a 1.5 molar solution and that it has a volume of, let's see, 50 milliliters. So 50. You go through there, you calculate V1, you should get is 9.375 milliliters. To figure out how much water you're adding, we have to do 50, that's the total volume of the solution in the end, minus our original volume, 9.375. And you get 40.625 milliliters of water added. right, question number 16. So this one says, if you mix 25 grams of NaCl into 100 grams of water, what's the new freezing point? What's the new boiling point? So on this one, it's a freezing point, depression, boiling point, elevation type problem. You get the constants on the test. Something you need to know is how to calculate the Van't Hoff factor, so make sure that you're good at that. NaCl has a Van't Hoff factor I equal 2. All right, and so what we're going to do here first, because molality is needed here, and molality is the moles of solute in kilograms of solvent, we have to find out how many moles we've got. So we start with 25 grams of NaCl, and then there are 58.44 grams of NaCl and 1 mole of NaCl. You calculate that, you get 0.428 moles. All right, so then we have to calculate the molality. Molality equals, as I said, moles of solute over the kilograms of the solvent. So that's 0.428 over 58.44. Oops, that's not correct. The kilograms of the solvent, it says it's 100 grams of water. So 100 grams is 0.1 kilograms. All right, and so you have to make sure to have that in kilograms. We divide that there, we get 4.28 molal. 4.28 molal. All right, now we need to find the actual freezing point and boiling point of this. So to do that, you say delta Tf, change in freezing temperature, equals I times m times Kf, the freezing point constant. So Van't Hoff factor here we said was 2 because NaCl is ionic, and so it's going to split into 2 pieces. 4.28 is the molality, and then the Kf is negative 1.86 degrees Celsius per molal for water. So if you calculate that, I get negative 15.92 degrees Celsius, which means that Tf equals negative 15.92 degrees Celsius. Now it's important that you see actually there's a distinction here between when we said negative 15.92 degrees Celsius the first time and when I said it the second time. The first time is your change in freezing temperature. The second time is your actual freezing temperature. With water, the normal freezing temperature is 0. So if we have it at 0 and we change it by negative 15.92, we end up at negative 15.92. You'll see something different happening sort of with the boiling. So change in boiling temperature equals I times m times Kb. Van't Hoff factor is still 2. Molality is still 4.28. All right, the Kb, the boiling point constant, is 0.51. We multiply all those, we get 4.37 degrees Celsius for our change in temperature. And so the normal boiling point is 100 for water. And so if it's 100 and it's changing by 4.37, then the new boiling temperature is 104.37 degrees Celsius. Number 17, it says what molality of chloroform would need to be dissolved in 2 kilograms of water in order to depress the freezing point by 3.5 degrees Celsius. So on this one, we're talking about freezing point depression. Because it's chloroform, which you can see here has a formula of CHCl3. Those are all nonmetals, which means it is a covalent molecule. It's not ionic. It's not going to spread out or dissociate when you put it in water. So our Van't Hoff factor equals 1 for this one. All right. You know delta Tf equals I times the molality times Kf. things we know here, it says the freezing point was depressed by 3.5 degrees, so change in freezing temperature is negative 3.5 degrees. I is 1. The molality is what we're trying to find. So that's our variable. Freezing point constant, negative 1.86. Now here, notice the 2 kilograms of water actually didn't matter at all because I'm asking what the molality is. I didn't ask for the number of moles. If I'd asked for the number of moles, then you would need to go and use that 2 kilograms for the molality. But yeah, since I just want m here, you can solve it directly from this formula here. You divide both sides by negative 1.86. You get that the molality equals 1.88 molal. For the last problem here, it says 7.84 moles of a mystery solid are dissolved in 6 kilograms of water. The new boiling point is 102. What is the Van 't Hoff factor of the solute? So this one we're trying to find I. We're trying to find that Van 't Hoff factor. And so molality, here we're going to find first 7.84 moles. It says 6 kilograms, so 6 kilograms. That's 1.31 molal. All right, and then you know change in boiling temperature equals I times m times kb. In this case, as I said, we're looking for I. It says the water is boiling at 102, so that means that change was 2. I is what we're trying to find. The molality was 1.31. The kb is 0.51. And so what you'll do then is just take 2, divide it by 1.31, divide it by 0.51, and you get I equals 2.99, which is approximately, with rounding, equal to 3. All right, that is that. Please look through all your review materials, and if you have any questions, try and come in and talk to me before you take the test.